Hey, welcome to The Explainer. Every single thing we plug in, every light we switch on, it all works because of this invisible world that's, believe it or not, running on a really clear set of rules. Today, we're going to decode those rules. And the key we're using to unlock it all, well, it's a little unexpected.
So, our guide for this whole thing is an actual electrical technician's exam from Korea. And no, don't worry, we're not studying for a test here. Think of it more like the questions and answers are clues. They're the keys that unlock the fundamental principles that power, well, everything, our entire modern world. So yeah, let's dive in and see what secrets we can dig up. All right, so where does this exam tell us to begin? Well, it starts at the beginning. Before you can build anything, you got to understand the basic forces at play. We're about to dive into the foundational laws that govern every single spark and every bit of current.
And the absolute ground zero, the starting point for all of this, is Coulomb's law. Our exam, specifically question 21204, makes it clear. If you want to know the force between two little electrical charges, whether they're pushing each other away or pulling closer, this is the fundamental rule. You can kind of think of it like gravity, but for electricity. Now, this leads right into something we call voltage. The easiest way to think about it, it's like electrical pressure. And question 21203 in our guide gives us a perfect example. It's basically asking about the potential difference between 2 points. The answer comes out to 90 volts, but that's not just some random number. It literally represents the amount of work or push it takes to move a charge from one spot to the other. Okay, let's talk about scale for a second, because it gets wild. Question 21207 asks for the value of one single electron volt, and it's this number. Yeah, that is an incredibly tiny amount of energy. But here's the thing. It's the fundamental currency of the atomic world. Every electron zipping around in a circuit, it's carrying its energy in these just unimaginably small packets.
So with all these forces flying around, how do you protect sensitive electronics? Well, question 2110 introduces this really brilliant concept, electrostatic shielding. The exam gives this great analogy of putting a metal mesh over a detector. That conductive cage, it just intercepts any external electric field and creates a totally safe zone on the inside. This is exactly why your important cables, like for audio or data, are shielded. It's basically a tiny Faraday cage doing its job.
Okay, so we've got the laws down. Now let's see what happens when we actually use them to build stuff. This section is all about the practical math, connecting components and actually making electricity do what we want it to do.
Okay, check this out. If you line up resistors one after another in series, you just add them up. Super simple. But as question 2122 asks, what happens if you put them in parallel, side by side? Well, the math gets a little weird. You got to add the reciprocals and then flip the whole thing back over. But here's the key takeaway, the counterintuitive part. Adding more resistors in parallel actually lowers the total resistance. It's like opening up more lanes on a highway. You're just giving the current more ways to go. All right, now let's see how all these ideas start stacking on top of each other. Question 21117 throws a much more complex AC circuit at us. It's got resistors, coils, and capacitors all in the mix, kind of working together, but also kind of working against each other. So to find the current, you first have to figure out the total opposition, which has a cool name, impedance. And what's really neat here is you can see how the effects of the coil and the capacitor actually cancel each other out a bit. You just plug in the numbers, use good old Ohm's law, and bam, you get your answer, 2 amps. This is bread and butter stuff for electrical engineers. Then question 2122 brings up a really critical distinction. See, most of the basic parts, resistors, coils, capacitors, they're what we call linear. That just means if you double the voltage, you double the current. It's a simple, predictable, straight line relationship. But then you have the nonlinear components. The exam mentions vacuum tubes, but think modern transistors. Their response is not a straight line. And that little detail, that nonlinearity, that's the secret sauce that makes all the complex switching and amplifying in our digital world even possible. Okay, let's get to the other side of the coin. Because you really can't talk about electricity for long without talking about its inseparable twin, magnetism. Honestly, this is where the real magic happens. This is how we get motion from power and power from motion. And this right here, this is the core principle. Question 2113 lays it out perfectly. If you move a magnet near a coil of wire, or even just change the magnetic field that's passing through it, you generate a voltage. Poof! And the crucial part is, the more turns you have in that coil and the faster you change that magnetic field, the more voltage you get. It sounds simple, but that single idea is the foundation for pretty much every power plant generator and every single transformer you see on a utility pole.
So how on earth do you keep all this straight? Which way is the current going? Which way is the force? Well, question 2129 points us to Fleming's handy rules. It's like a little cheat code. If you want to figure out power generation, you use your right hand. That's your generator. If you want to figure out how to create motion, you switch to your left hand. That's your motor. It's the same physics, just a different application, and the only thing that changes is which hand you use. It's just so elegant. But here's a wrinkle. Not everything reacts to magnetism in the same way. Not even close. As we see from question 21215, materials basically fall into 3 buckets. First, you've got your ferromagnetic stuff, like iron. They're strongly attracted to magnets, the ones we all know. Then there's paramagnetic materials, like aluminum, which are, kind of weakly attracted. But then you get the really weird ones, diamagnetic materials, things like copper and antimony. They're actually repelled by magnets. Wild, right?
So let's say you want to build an electromagnet, right? Like one of those massive ones that lifts cars in a scrapyard. How do you know how strong it's going to be? Question 2178 gives us the formula for a long coil, what's called a solenoid, and you're going to love how simple this is. The magnetic field strength H is just the number of turns per meter, N, times the current you're pushing through it, I. That's it. That's the whole formula. You want a stronger magnet? Add more turns, or crank up the current. Simple.
All right, we've covered the big picture laws and the invisible forces. So now let's zoom in on the actual physical parts that make everything work. These are kind of the unsung heroes, tucked away inside every single device you own. So let's look at 2 different types of capacitors that pop up in the exam. First, question 21214 talks about the ceramic capacitor. This is your reliable workhorse. It's cheap, it's common, it's everywhere. But then, question 212005 introduces us to the varicon, which is a variable capacitor. By physically moving its plates, you change how much they overlap, and that changes its capacitance. This is literally how old-school radios used to tune in to different stations. So you've got 2 capacitors designed for 2 totally different jobs. Okay, here's a great little trivia question for you, pulled straight from the exam. Think about a standard car battery, a lead-acid one. Inside, it has a positive plate and a negative plate, and they're made of different stuff. But question 21206 asks a simple question. What happens when that battery is completely discharged? Totally dead. What do both of those plates turn into? Lead sulfate. That's the answer. When the battery discharges, a chemical reaction happens that coats both plates in that exact same substance. And once they're the same, well, the difference between them is gone, and so is the voltage. The real magic of recharging a battery is just that you're forcing that chemical reaction to run backwards, turning the lead sulfate back into the original plate materials and making them ready to provide power all over again. So what have we actually decoded from this Korean engineering exam? We've basically uncovered the 4 main pillars of electrical engineering, right? We started with the fundamental forces, the absolute basics. Then we learned the mathematical rules for how circuits work. After that, we explored that incredible link between electricity and magnetism. And finally, we got to meet some of the specific, purpose-built components that make it all happen.
You know, the principles we've gone over today, most of them were discovered more than a century ago. And yet, they literally built the world we live in. Which kind of leaves us with one final big thought. What are the fundamental rules being figured out right now in things like quantum mechanics or materials science or AI that are going to become the basic everyday knowledge for the engineers building the world of tomorrow? I mean, what's going to be on their exams? Thanks for watching.